Most processes in our universe are time reversible. In other words, the physics works the same way forwards or backwards, which is why you can't tell if I'm playing these videos normally or in reverse. People typically point to entropy as the only exception to this rule. The second law of thermodynamics states that the entropy of a system, or the amount of disorder, always increases with time. But increasing entropy is an emergent property, the result of the motions of many particles, which raises the question, can fundamental particles themselves tell the direction of time? Or in other words, is there a physical process on the scale of individual particles that looks different forwards versus backwards? The answer, surprisingly, is yes. In particle physics, there are three major symmetries that we're always expected to hold: charge, parity, and time. Time symmetry, as we've already discussed, means interactions work the same way forwards or backwards in time. Charge symmetry means interactions are unaffected if all the charges are swapped. In other words, there is nothing special about what we call positive charge. Nature treats it exactly equal and opposite to negative charge. And parity symmetry means the laws of physics are indifferent to left or right-handedness. Now, to understand what that means, imagine a giant mirror were held up to our universe. And in the mirror, the z direction is reversed and my right hand becomes my left hand, but the laws of physics shouldn't care. I mean, they should work exactly the same way in the mirror world as they do in the regular one, with no preference for left or right-handedness. Or to put it another way, there should be no experiment that you could do that would tell you whether or not you are in the mirror world. Each of these symmetries is known by its initials, C, P, and T. In the 1950s, it was thought that all fundamental particles obey these symmetries. But then in 1956, a paper written by Li and Yang pointed out that parity symmetry had actually never been tested in experiments involving the weak force. So at Christmas break that year, physics professor Xianxiang Wu of Columbia University had planned to go on vacation with her husband, who was also a physicist, but instead, so intrigued by the possibility that the weak force might violate parity, she decided to stay behind and be the first person to test it. To do this, she and a team of low-temperature scientists cooled a collection of cobalt-60 atoms to just 3,000th of a degree above absolute zero. Then they applied a strong magnetic field to align all the nuclei with their spin pointing in the same direction. Now, cobalt-60 is radioactive, and it decays via the weak nuclear force, releasing a beta particle, which is just an electron. And what the experiment measured was the direction in which these electrons were emitted relative to the spin of the cobalt-60 nuclei. To see how this would work under parity symmetry, let's consider the mirror image version of this experiment. In the mirror, the direction of the z-axis is flipped, but the direction of nuclear spin is not. That's because an object that's rotating clockwise is still rotating clockwise in the mirror. So, this means that the spins of the regular and mirror nuclei are aligned. The mirror experiment is actually the same experiment as the original. Now, when a cobalt-60 nucleus decays and emits an electron, that electron could go, say, to the left or to the right. Now, if parity symmetry is respected, the electron should be equally likely to go in any direction. That way, both the normal and mirror image experiments would give the same results. However, if the electrons were emitted in one direction preferentially, say in the positive z direction, well then in the mirror experiment the electrons would also have to fly off preferentially in the mirror positive z direction, which is opposite to the original positive z direction. So in the normal experiment the electrons would be emitted, say, opposite the direction of nuclear spin, but in the mirror version they'd be emitted in the same direction as nuclear spin. So how does this make any sense? It would allow you to determine whether you're in the mirror world or not. It's like the spinning top from Inception. If the electrons from the cobalt-60 nuclei go one way, you're in mirror world, and if they go the other way, you know you're in normal world. Now, crazy as this may seem, this is exactly what Professor Wu saw. Electrons were emitted preferentially in one direction, and not just by a little bit. They were predominantly emitted opposite nuclear spin. So not only does the weak force violate parity, it comes close to violating parity as much as is physically possible. This destroyed a basic assumption of theoretical physics that had been around for decades. Somehow the universe cares about left or right-handedness. When Wu announced her results, they shocked the physics world. After being told of the experiment, famous physicist and Nobel laureate Wolfgang Pauli said, "That's total nonsense," and insisted the result was mistaken. When the experiment was independently replicated, theoretical physicists had to accept that the universe we live in is not the one they had imagined. The Nobel Prize was actually awarded for the discovery of parity violation in 1957, the very same year these results were published. This required a profound shift in thinking for physicists, but before throwing everything out and starting again from scratch, they formulated a workaround. Maybe it was okay that the weak force broke parity, because it's not a real symmetry of the universe itself, just part of a larger symmetry, charge parity, or CP symmetry. The idea was if the mirror flipped not only these axes, but it also swapped the particles for antiparticles with their charges reversed, well, then the symmetry would be restored and the mathematics behind our laws of physics would still work. Now this gave physicists some comfort until in 1964 it was found that some particles can also violate the combined charge parity symmetry. And boom, you got yourself another Nobel Prize. Now two rules which physicists once thought were fundamental laws of nature were broken. So they retreated behind their last set of theoretical defenses, the combined symmetry of CPT, where T is time. Sure, they said, the weak force violates parity and charge parity, but certainly not charge parity and time together. And to this day, physicists are still pretty sure that CPT is a real symmetry of the universe. So far, no experiment has found a violation of CPT. In fact, if CPT is violated, we would have to rewrite a lot of the last century's work, because it would mean that special relativity and quantum field theory are both wrong. Okay, so let's say that CPT is a true symmetry. Think about the implications of this. If we know that CP can be violated but CPT cannot, then time symmetry must also be broken. Otherwise there would be no way for the combined three-way symmetry to be maintained while two of the subsymmetries are broken. And physicists have actually conducted experiments that confirm that certain particles directly break time symmetry. For example, when a pair of quarks are held together by the strong force, there are sometimes two different possible arrangements, and they can switch back and forth between these two arrangements via the weak force. But switching in one direction takes longer than switching back. So if you could make a recording of this event, it would look different if you played the recording forwards than if you played it backwards. And that's exactly what it means to break time symmetry. In certain cases then, fundamental particles can tell the difference between going forwards and backwards in time. The second law of thermodynamics is not the only physical process that prefers one direction in time. Now, is this the origin of our perception that time only goes one way? Or is it the reason for the universe's arrow of time? The truth is that we still have no idea why time only goes in one direction. What's interesting is that physicists once thought that parity, charge, and time were these symmetries that were unbreakable. But over time, each of these symmetries was demonstrably violated. So is the ultimate symmetry, CPT, also unbreakable? Or will it fall, taking quantum field theory and special relativity with it? These are just some of the big, basic, unresolved mysteries left in our quest to understand the universe. Perhaps one day, another physicist will give up their vacation to figure out the answer. This episode of Veritasium was animated and co-written by my friend Jorge Cham, who is also the creator of PhD Comics, and now he's written a book.
Yeah, it's called We Have No Idea. It's a book I wrote with physicist Daniel Whiteson, and it's about all the things we don't know about the universe. All of the big things like dark matter and dark energy, but also all the little things like what are all those fundamental particles for?
And it has cartoons in it.
Yep, and lots of bad puns.
So if that sounds like it's up your alley, you should check it out. I'll put a link to it in the description and all of Jorge's other projects.
Thanks.